Okay. So any questions about the course? Anything you want me to, actually, anything in particular you want me to go over when it comes from architecture hardware level? I do like to integrate if you have something you're really interested for architecture. Or if this is the, I don't care how a machine's put together, I just want to use it. I understand some students have that mentality, but some people are like, I really want to look at embedded chips or an ARM chip or build circuit board, or maybe I really want to learn about how meltdown happened or whatnot. Nothing, guys? It's 9:30. I'll give you plenty of time.
I don't have that much experience with this, so I don't really know what that's how to do.
Okay, I understand. Think of it more as, most of the time we were talking about, web development or a desktop app. If there's something else you're interested in, like an embedded device, in your car, your phone, anything, metal equipment, you care about hardware security as well. Those are the type of things we're going to be focusing on. But I understand at this point it might be a little over, you don't know what to ask. Anything in the news? Ooh. I guess y'all are into architecture. Any architecture news? Graphics cards count as well, by the way. Yeah, the thing I noticed is they're really pushing ray tracing right now. Which the ray tracing is nothing new. It's just been one of those things that the hardware can never handle. But usually I don't care about graphics, but the ray tracing does look pretty nice.
What is that?
It's the idea is that, so normally when let's say you have a car right here and then they make a flame, normally they fake a flame image on top of the car, is the old way. Ray tracing is it's a lighting source, so they're going to take the rays and trace it as it hits the car and bounces off. But in order to do that, you have to trace a ton of rays in order to get an authentic look, as opposed to just plastering an image on it.
That's cool.
The computational power for that is way more significant than just plastering an image, but the final product looks way more authentic. So this is one of the things where I think it's going to start looking really close to real life. It's going to be hard. It's going to start being hard to tell the difference. Because before then, even on really high resolution, I could just tell that they just plastered a fire image right there or something. But that's one cool thing that's coming up. Anything else?
Apparently Intel put out a plan, like in the future, they want to hit 1.4 nanometers by 2029.
Oh, okay. 1.4.
Mm-hmm.
Nice. That's their plan.
Apparently their plan is to go, they're working on going to 7, like AMD, and then 5, 3, 2, and then 1.4.
1.4. 5, 3, 2, 1.4. Wow. Wow. So, little backstory there. Intel, by the way, has just been the market king for ever, basically. It's been ever since was it 1980 when the 8086 and then the 286. Once that came out, they just started crushing the market, and they've basically been the giant that just been crushing it. And Intel has been just nipping at their heels, trying to get market share. But it's really this last processor where Intel or AMD pretty much for the first time has surpassed Intel, because they have the lower process, 9 or 7 nanometers. I think Intel, are they on 14 or 10?
I think they're on 10 right now.
I think they're, okay, so they did get down to 10. So AMD is able to put more area on their chip, and they're definitely taking advantage of that with lower power, more cores, and so their multi-threaded chips are faster than Intel, although Intel is still slightly faster on single thread performance.
There was something Intel was using AMD to test their new hard drive or something because it didn't have PCI 4 or something.
Yep. Oh yeah. AMD now supports PCI Express 4.
So
Intel's still on 3.
Yeah. So they were trying to do their Octane or whatever. So I don't understand what that
That's their SS. So what they do is, because you have your solid state drives and then you have your MDM, those little chips.
The little tiny ones,
yeah.
right?
And so what Intel will do is they'll have their Octane, which goes into a PCI Express 4 slot, and it'll be faster than either of them.
But what is the Octane? Like
That's just that's their name for it, the SSD that plugs into
it's
a
like, oh, it
PCI 4.
boosts your memory. Like,
Right.
That's
They
just
call
marketing.
it they call it hyper-threading. That's just
Yeah.
simultaneous multi-threading, which we'll get to in this course. They just rebranded it so it'd be awesome because it's Intel, right?
They make it sound like it makes
Yeah.
your computer
It does help,
faster.
Oh, it sells.
Yeah.
Oh, it sells.
It makes
I
it
just
sound
bought
like
the
it
PC
doesn't
because
just
it had other
just
specs I
hardware.
needed, but
Yeah.
it's like, it's a bonus. I
It is
guess.
about no hyper-threading helps. It does help. I'm not saying it doesn't. It's called simultaneous multi-threading. They just called it hyper-threading just to be that way.
Yeah.
Well, it's easier to say hyper-threading than simultaneous
Multi-threading or SMT.
Yeah.
I mean, SMT is a nice TLA. 3-letter acronym for those who
Yeah.
didn't catch that.
People love their
Their TLAs.
Military and IT.
Okay, so things are still competing in on the chip market, which is always good. Also, DDR5 should be coming out this year.
No, I don't want to buy that. Actually, hasn't like NVIDIA been using that? Or is that different? Like
They use DDR6 in their cards.
Are they
Oh, that's
the
so
same?
that's something different. It's called GDDR, and I forget what that maps to. I'd have to look it up.
Okay.
But they also use HBM, high bandwidth memory, which is way faster than DDR, but it's super expensive. So not very like if you buy a $2,000 graphics card,
Yeah.
it'll use HBM.
What's
but-
DDR5 is supposed to be? How much better is that supposed to be?
It's going to be more than twice as fast as 4.
Is like the clock speed in it?
Right. The clock speed's going to increase, but they're also going to increase the bus on certain aspects so they can push more through per clock as well, and they're rearranging a couple of components as well. So there's a lot of little things that are coming together for DDR5.
Fancy.
Yeah, pretty
I only
fancy.
just got DDR4. I had like a 5-year-old motherboard until
No.
it died. So.
Well, don't worry. DDR5, it'll probably come out later this year.
Dance Dance Revolution. Man.
Yeah, that's what stands. That's what I thought of when I first started too. Like, yeah, DDR. Like, no. Okay. So below your program, this is one way to think about how your program executes on your machine. The application software, that is the program you've been writing or you're running. Photoshop, your game that you might have, or Visual Studio. That's an application. But underneath that is the system software, aka your operating system, and that's usually composed of libraries, standard C libraries or other libraries, as well as your kernel, which is the kernel is the piece of software that executes closest to the hardware and interfaces with the hardware. So the OS kind of has 2 levels, which we'll get to, and then it actually executes through to your hardware. This is important to realize because when you try and do something through application, it has to go application, system software, hardware, then it comes back from the hardware through your system software and then to your application. So there's down and back up. And this is a very high-level view because usually application, it might just be 1 layer. Your OS might be 5 layers. Your hardware, who knows how many layers it is, depending on what you got. Because it might have to go through your PCI Express bus to find the right card, select the correct card with the right lane, go on the motherboard or the board of your video card, and then who knows what that's using, and then finally go out. So there's a bunch of layers to all this that it must move through in order for something to happen. All right. So a compiler translates your high-level language code to machine code. I know this may seem weird, but C is a very high-level language because it's way easier than assembly, and we will get to that in this class. Oh, here we go. Perfect. So take your high-level language, aka C. Compiler translates it to assembly. That all looks crazy, and then the assembler changes it to the bits, the binary code for it to use. This picture is in MIPS. I couldn't find an x86 one, so just deal with it. These will be different when it goes into x86. Your C is still the same, but your assembly is different, and your assembled binary language bits will be different. Not that this means anything to you, because it doesn't to me. All right, your CPU, which is what does the processing or the decisions in your computer. Some people like to refer to it as the brain of your machine. It has a data path where it performs the operation of the data, and then it's going to have control whether it decides what to do, because you write your if statements. Your if statements are your control, and your data is your different integers, doubles, so forth and so on. And then it has cache memory, which is basically, think of it as like a scratch pad of it trying to do something real quick as opposed to having to go all the way out to main memory, because main memory is incredibly slow, as we will get to. Oh good, we get a look at architecture pictures. All right, so this is the Intel Haswell, which I believe is their latest i7, if I have that correctly. Skylake? One of their no, I'm sorry. This is Skylake. Haswell is their 4th generation.
Yeah, 'cause
But this is Skylake. This is, I just mislabeled this.
Okay, because I had Haswell.
Yeah, sorry
before
about
it
that.
died, and it
Yeah.
was 4th gen. Okay.
This is Skylake. Thank you for the correction. Haswell is 4th generation. Skylake is the 10th
I
generation.
didn't know if that's in the
Yeah. But I know that I updated this picture because I did it yesterday. And this is different than the Haswell picture. So a couple of things to notice. First off, well, just reading it, what do you notice about this? How many cores are there?
Got 6.
We've got 6 cores, and that's just been steadily increasing. Was it mid-2000s, maybe late 2000s? A lot of chips were just single core, so now we have multi-core. I know this L3 $ sign doesn't mean anything, but this is memory, as well as pieces of these cores are memory as well. You want to know what? How about this one over here?
You're talking about the built-in one, like the Intel HD, whatever it is, 1000?
Yeah.
I guess
Well,
that's what they're on now.
So, well, GPU.
Yeah. Is that the same, if they were to have like a built-in one, would it be in the same spot? Like you have some have like NVIDIA built into the motherboard where it
Oh,
might
into
be
the
somewhere
motherboard?
different.
Now, if it's on the
Integrated,
motherboard.
or integrated versus like a national.
So the ones that are integrated are on the motherboard as
Oh,
opposed to
nice.
being on, yeah, usually, well, it depends. It depends.
Okay.
The Intel ones in general, or the NVIDIA ones, sorry, the NVIDIA ones are generally on the motherboard. The AMD ones are able to put them on a chip because AMD controls, well, they bought out ATI, so they make their own chips.
That's
So they,
what I was
yeah, that's what you're thinking.
Okay.
Yeah. But Intel does have GPU capabilities inside their chip as well.
Okay.
Very important distinction here. This is these are 6 processing units that are essentially the same. This processing unit over here is very, very different. So your chips are containing different types of processing. Why would that be the case? They're right. It's a different problem to
A
solve.
lot of different things to do.
As we will find out, or as people have found out, depending on your problem, different architectures are better suited for it. GPUs are what's called embarrassingly parallel, so you can have very wide, or we'll put it differently. You can have many functional units to do all the processing, as opposed to CPUs, which have to spend a lot more time evaluating if statements and control logic, while a GPU is really just a giant machine you push numbers through. You got a system agent, and that's how it communicates to everything off board. So your PCI Express, as well as anything else that might be on there. And then of course your memory interface to talk to main memory. All right, well that was nice of Intel to tell us everything. Apple looks a little different. That might be a little harder to see.
I hope they still use Intel.
They do. They call them Thunder and Lightning CPUs for some reason. I don't know why.
They gotta name everything something different.
they got, yeah, it's like hyperthread, right? Hyper.
Oh, we got our Thunder port.
Yeah. So up here, notice again we have caches. What's nice about this one is the caches look very unique. There's one here, they don't show it here, but here's some other ones, some bigger ones. These are regular x86 CPUs. But notice over here, this is an Apple A13, which I think goes in their iPads. Is that right?
I think it goes in their iPhones too.
iPhones as well? Okay. Oh, well, that would make sense. So they probably disabled these guys and just powered the smaller ones for most of the time. That would, what is an NPU? Ooh, anyone?
It's not networking.
Nope, try it. What's the big thing now on your phone? Take a picture of something and it tries to identify what it is. So remember the machine learning?
You mean like neural?
Yeah, so it's a neural processing unit.
For
Yeah,
like
so
AI.
yeah, so they actually have a processing unit dedicated to doing this type of neural processing.
Like the open your phone with
Mhm.
your face.
Yep, yeah, you got it.
Got
Recognize
it.
your face.
It's got its own thing to that.
It's got, yeah, they now have their own core.
It's ridiculous.
Ridiculous. So from security, real quick, guys, this is all on the hardware level. If you compromise any one of these systems, you're on the chip. You can then pretty much interface with someone else.
Whatever.
Right? So the more architectures you add here, that increases your attack surface or your entry points into the chip. And so now you have to, this is why on security, if you just disable some of these chips or cores, it's better. But that's not always going to happen, because if you try and do GPU on your CPU, I don't know how many people have tried that before, it doesn't go as well. But, and I would imagine that same thing with MPUs, although I have not looked into that too much. That's pretty new.
Okay,
I don't think that was on the
yeah,
A12.
Oh.
Okay, how's everyone doing? This is the giant overview. You got all this? How you doing, Holly? Great, thank you. All right, how do we store? There's volatile memory, and that loses instructions data when you power off. This is your RAM. You put stuff in RAM, you turn off your machine, it's gone. Non-volatile memory is your hard drive. Magnetic disk. Ooh, how many people still have magnetic disks?
Can't say
You know, spinning disks?
that. Oh, wait, no, I was thinking it's the You mean a hard disk?
Yeah, hard disk instead of an SSD.
I've got.
You got a couple? Yeah,
I've
so
got,
there's
I've
still.
got an extra one.
You've got both?
Yeah, same. I got.
OS runs on a SSD, but then I've got a larger hard drive to store stuff.
Store stuff? Okay, yeah, that seems to be the common case right now.
That's what I've got too.
Cool. So yeah, magnetic disks are still used. Interestingly enough, there is one use case where a magnetic disk is faster than SSD, and that is when you are writing a lot of data. So you're constantly writing to a drive. The magnetic disk stays consistent on its speed. The SSD is super fast and then just dovetails once you fill up the blocks. We'll hopefully get into why that's the case a little later. But
Is this sequential or is that something different? 'Cause that's hard to-
yeah, magnetic disk sequential continuous writes.
Okay.
The magnetic disk will always win,
Okay.
but it has to be continuous. As in, at first your flash memory is going to be way faster.
Yeah.
And then once you hit the point where you used up all your free blocks, it's going to slow
Okay.
down to a crawl.
Is it? Okay.
Yeah, we'll get to that.
Sequential and random.
Well, I would say once the
Okay, it's a
SSD
little
hits
bit
that
different.
wall, even random writes are going to be faster
Oh.
on the disk, because it just has to move ahead.
Do you mean like continuous, like it just keeps writing
keeps
for a long
writing,
time?
keeps
like,
writing.
I guess maybe servers.
Yeah,
if
you're writing a log.
constantly doing-
Yeah, you're right. Optical discs, so CD-ROM, DVDs. I guess I should really put the word Blu-ray there.
I don't know what that is.
You know what a disc is?
Disc.
Disc. I should bring my floppy disks in. All right, networks. Pretty much we use, Ethernet over LANs and WANs, although we can do it over Wi-Fi, Bluetooth. It's really hard not to call it the Wi-Fi.
I call it Wi-Fi.
The Wi-Fi. What do you call it?
Wi-Fi.
Wi-Fi. All right, technology trends. Okay. I don't know if y'all can see this. Relative performance per cost. So 1951, we all remember because we all have our vacuum tubes in our closet that we keep around, right?
Oh yeah.
Perry?
Sure.
Still there?
Still there. Excellent. Then in 1965, someone came up with this cool idea of a transistor. And that's like maybe we should bring those in. They look funny. And so you could call it, what was it? You buy 35 of them for the cost of a vacuum tube, and then someone came up with an integrated circuit where you could etch the transistors on a piece of silicon, and that was 900 to 1, so that's way better. And then basically from then on out, we've just come up with better and better ways to etch onto silicon to the point where it's something absurdly cheap compared to how long it takes a vacuum, a cost of a vacuum tube. But what's important is that this is a logarithmic scale, which means if it's going up linearly, your your cost is decreasing exponentially per transistor. So, and that has to deal with Moore's law. So again, it's becoming exponentially cheaper to fabricate the transistors. So now we got to figure out what are we going to do with all these transistors. What's that?
It's a Bitcoin money.
So we use silicon because it's a semiconductor. We will go into more of that actually maybe today or maybe not, depending on where we end up. We add material to transform it into a conductor, an insulator, or a switch, and then we use that in order to build our processors. How do we do that? Well, we get a silicon ingot, which is aka a giant silicon cylinder. We slice it up into wafers. And I'm just going to say 20 to 30 processing steps because it's very complicated what happens here. Well, that etches the processors into the wafers, something similar to that. You notice where the squares are, that's where each processor is. We test the wafer, and we find out which ones are bad. So we dice them up, dice up the ones that are good, and then we find out which one of those diced up ones are bad. We bind it to a package, then we test the package, see which ones are bad, and throw those away, and then we can finally ship to the customer. By the way, yes, there is a problem here with yield because a lot of these go bad because maybe your silicon ingot isn't completely pure. There's no way to we can't make a pure silicon ingot. It's just not feasible, but we can make it 99.999% pure. But that 0.01 is going to make something fail. And of course our dicer isn't perfect, so that's going to mess something up. Bounding to a package isn't perfect, so that's going to mess something up. So yeah, when you go into these fabs, they throw away a lot of chips because they failed. And there's a lot of research, and you'd be paying a lot of money if you can make these things even slightly more accurate and efficient. Yes?
Aren't a lot of chips like, oh, it didn't, this one isn't quite as like, it works, but it's not as fast as everything else, so we're going to sell it as
right. So what they do, a lot of what they do is they have their Hertz rating or their how fast it can run, and due to manufacturing, sometimes it can't hit a certain speed, but it can hit a lower speed, so they'll sell it for cheaper. Another trick they did with the PlayStation 3 is it had a CPU and then 8 streaming processors, but they had logic to where you only use 7 of them, and it would automatically disable the one that failed. And so that actually increased yield a lot because as long as your error was only on the one of the streaming processing units, your chip is fine because they only guarantee 7 of them. So there are tricks to it, but that cell chip was not an easy thing to program for. I guess y'all didn't program for that one. Yeah, it was a pain. It was a huge pain. i7 wafer might look something like this. Yes, I know there's no way you're going to get a processor over this little piece right here, so they just chop it off. It's just how it is. Okay, Verilog. We'll be using Verilog throughout this course. I highly recommend virtualizing Ubuntu and running everything from there. You can do iVerilog from Windows. I've seen it work, but I do just recommend Linux. Life is going to be better, especially when you try and integrate with GitHub. So first homework, please download iVerilog, also called Icarus Verilog, and be ready to start coding in class. If you're on a Mac, make sure you've been using Homebrew for everything, which hopefully is what you've been using. Good. Icarus Verilog is the open source free Verilog toolchain. I'm going to warn you right now, it is not the, definitely not the best, but it's free. If you want to buy one, some of them cost thousands of dollars. So please just deal with the fact of what it is. But the nice thing about iVerilog is how simple it is to use. Why Verilog? It's an industry language used to design processors. So we're going to be building a simplified x86 processor. x86 is a 32-bit processor, which is a root of virtually all PCs. Modern day CPUs use x86_64, which is a 64-bit extension of x86. I'm trying to make this simple, so we're going to stick with the 32-bit version because it is definitely simpler than the 64-bit version. All right, how are we doing? All right, we'll go ahead and start the next section.